Hello, class. Starting a little later today, but did some other stuff. A lot of important things going on all the time, as you can imagine. Yeah, I am not working on so many things. I have like 5 different jobs and so many other things that I just enjoy doing. Now, today I've got the way I want to start out this lecture is that this is really the beginning of what I would consider as a series of lectures now, where we're leaving what I would have considered originally was review, really. I mean, not everything up to this point, deriving the radial electric field around a line of charge, obviously isn't something that you probably ever saw before. And but I'm even assuming that you are aware of the exponential form. We're going to be using the exponential form a lot. And as a matter of fact, I originally, it took me a little while to put this lecture together because I thought that I would combine this lecture that I'm going to give you today on traveling waves. That I was going to combine this. I could never tell if there should be 1 or 2 L's in traveling, so don't ever tell me. I think it can be either. So anyway, today what I wanted to do was talk about traveling waves and to point out that, of course, electromagnetic waves are traveling waves, or how would they get here from the sun? And I also want to look at a phenomenon. I shouldn't say a phenomenon. And really, if you think about it, it's common sense that it would work this way. And I also want to introduce you to the communication circuit, but only in a tertiary way, because that's not really what I'm going to be talking to you about today is the communication circuit. Although I should draw the communication circuit, I want to draw a couple things. First, let's always from now on draw the communication circuit, shall we? Because that's what electromagnetic waves are. I mean, if you look at how we transmit electromagnetic waves to use them for communication, what are we really doing? We're putting them over metallic conductors, and this is what I'm drawing this for, is really metallic conductors. And I think I've even drawn this before for you. I don't know. This would be V in, and this would be V out down here. And of course, that would be R, C. I'm going to put a prime over each one of those because we usually refer to the resistance, capacitance, inductance, and conductance as, and we show this with the resistance here, but really what we're showing is that there is some sort of conductance from the signal wire. This would be my signal wire, and this would be my ground shield out here when we're thinking of metallic conductors. Now, whenever we're thinking, and I say metallic conductors, but this also includes transmission through the atmosphere, right? And when we're transmitting electric fields through large transmission lines, in between transmission lines, this is the different phenomena that are at work to attenuate the signal as it moves from the location at V in to the location at V out. What are you doing? Get back in focus. Woo. Focus, focus. I don't know. It'll come back. Probably not. Anyway, so let's talk a little bit more about that. If I've got this and I've got an input here and an output here, then I really have my signal, right? V sub G, I'm going to call it. Let's say that I've got some type of AC waveform, and then I'm propagating this through, right, my communication system that I've got here. I'm going to call this A prime. So I'm at this location, and then I'm going to set up my input, you know, over this long communication wire, right? I'll just draw something like that. I saw this in a magazine once, and I always wanted to do it. So, but now it looks like SS signal. Yeah, I think I drew that wrong. But anyway, now it doesn't, thank God. So then going down to B prime, another location, let's say 10 kilometers away. Come on, snap back into it. I'm going to have to, oh, there we go. Oh, that's good. Okay, now this is going up to B prime. And of course, as we're running along here, we've got resistance, we've got, you know, inductance, capacitance all through there and everything else. Don't worry about that. What I'm worrying about is this distance right here. I'll call that distance L. So let's say that distance is 100 kilometers. It's 100 kilometers maybe. I don't know, but it's a long distance that we're transmitting this over. Maybe we're talking about you know, the old trunk lines that they used to have for the telephone system. Well, they're all fiber optic now, but you know, so we've got a distance here, and this applies. Now this would apply to fiber optics because they're not traveling faster than the speed of light either. So whatever, just two things that are a distance apart. All right. Now, if that distance is L, then let's say that the voltage that's going in there, or the voltage at A prime, I can say is going to be my gate. I call it my gate voltage as a function of T. And I'm going to say that the voltage coming out of there, it's an AC waveform, is going to be V cosine omega T, right? And that's where that starts. And now, before I finish off what my voltage at B prime should be, let's look at the voltage. And actually, let's use some real numbers so that we can sort of see what is going on here. And I'm going to draw this down here because I'm going to be referring back to it. I suppose I should draw it more up here or whatever, but yeah, why don't I? Why don't I draw it up here? I'm gonna, I'll start it out here. I'll start, excuse me. And then, let's make this the timeline that I've got there. Then I'm just going to draw a waveform. Did I do that right? Yep. All right, does everybody see that waveform? Now what I'm going to do with that waveform is I am going to extend that waveform back in this negative time direction too. All right, so this is the future. This is the future. This is what's already happened. Now, let's just look at that waveform, right? Now, we know a couple things about this waveform, and this is why I wanted to take a full lecture to talk to you about this. right? This is an electromagnetic wave that is traveling down something. Doesn't matter where it is. Could be through the atmosphere, heading to the antenna on your car, whatever. But as you can see, this wave that I've got right here is a function of not only x, but also of t, isn't it? Does everybody see that? No, you don't see it, and I'm going to tell you why. Because they don't have 3-dimensional, 5-dimensional, or 4-dimensional things yet. But, and you probably saw me carrying this thing around, I was thinking to myself, now, if I was stranded on a desert island and I had to come up with a lecture for electromagnetic field theory, I guess there wouldn't be anybody to give it to, but of course it'd probably be insane being on a desert island. Yes, I am. So let's go back to this. Now, let's look at that waveform, the waveform that I drew there. Can everybody see that the voltage along this waveform is changing with x? Does everybody see it's changing with x? You know, it's 1 right here. In fact, it's changing with x, but this is moving at the same time, isn't it? So this is moving in this direction at the same time, at the speed of light. It's moving in this direction at the speed of light. Now, I'm sure that I'm saying this and I'm thinking to myself, it could be an epiphany to some of the students that they didn't even know that this is exactly what was going on, that it's changing in x and it's changing in t. Obviously, it's changing in x right now, right? Come on, get out, get back in focus. There you go. But the wave itself is traveling in that direction at the speed of light, isn't it? So it's changing in time and it's changing in x. It's a thing that's already different in x, but it's changing in time. Now, how do I represent that at voltage at B? Well, the voltage at B then is going to be V0, just like it is here. We're using the same magnitude and everything else, and we're using the same frequency. And it would be the cosine, but it would be the cosine of omega, right? But what's the time? What's the time difference at B? What would the time difference at B be? Well, it would be, of course, omega t, just like we've got up here. Cosine omega t, cosine omega t. But this one would be wave shifted L over the speed of light, because doesn't it take that long for the wave to have traveled? Right. Now, what I want to do, and remember, and that's why I want to bring this out, we've got the wave here. Now, this is what I'm going to say. The wave where it is now in black, the wave where it is now is at t equals 0, right? At t equals 0. And that's a special case. So let's look at that. So at t equals 0, VB B prime is going to be V0 times the cosine of minus omega L over C. Does everyone see that? That's a special condition, and that's the condition that we're going to look at right now. Because it's one thing to tell you and to get some wire that you found on your deserted island and say to the students, hey, you know, not only is it changing with x sinusoidally, as you can see right here, but it's also going to change with time, because in time, this is a moving wave, right? It's a moving wave. Now, I want to put some numbers to this so that you can actually see how this all works out too. So I'm going to say that we're going to use a wave, I'm going to look at a wave that is 75 kilohertz, right? 75 kilohertz radio wave. That's what you want to think about. So we've got it'd be a short wave. It'd be, so we've got a 75 kilohertz wave traveling through the atmosphere. I wanted to make this, I didn't want to throw extra stuff in there, changing the velocity of propagation. This is traveling through the atmosphere. Now let's say that I'm sending this, you know, like 55, 60 kilometers away to another microwave tower, right? Well, which can't say really microwave, what am I saying? Radio wave tower. So I'm broadcasting this. In fact, 75 kilohertz could go a lot further than that. 75 kilohertz could go all the way around the world. So let's say I'm broadcasting this to something 10,000 kilometers away. Fine, whatever. It's all going to stay the same, because now that we've got the frequency, we can easily figure out what the period is going to be for one cycle of that frequency, isn't it? That, of course, is 1 over the frequency, and that is 13.333 microseconds. And that's for a full period, for a full frequency cycle. So here would be my first cycle. Does everybody see that? I'm going from 1 down and back up, so that completes my first cycle right there. So that would take 13.33 microseconds. And you're probably also wondering, well, okay, that takes 13.33 microseconds, but how long is that, right? How long is that wavelength for a 75 kilohertz electromagnetic wave? And we know that frequency times wavelength equals the velocity of propagation. And in this case, the velocity of propagation through the atmosphere is the speed of light, right? Why is that doing that? Come on, snap back in there. All right, so it's the speed of light. It's because I'm writing on there, I guess. I don't know. I've got the lights on and stuff. Maybe I should, maybe I can open this up. Maybe that'll help. Just a second. Sometimes I leave this open and it seems to bring in more light. And it's not a real sunny day, so maybe that will help. It looks a little brighter. Okay. Now, all right, let's go back. No, it didn't have it. All right, let's go back to this then. So the wavelength then, since we know the frequency times the wavelength equals the velocity of propagation equals the speed of light, then we can figure out what the wavelength is, because it's just the speed of light divided by the frequency, right? So in this case, the speed of light divided by the frequency, why did I write wavelength, is going to give me 4,000 meters. Does everyone see that? Yeah, you know, that doesn't look very good. Let's see if I can make that look better. Yes, it's supposed to say frequency, so there we go. Yeah, it always said frequency. So the wavelength is speed of light divided by frequency, and that's going to give me 4,000 meters. So we also know now, and I can only use the blue one because I still have not found the other one. Let's just look at a variety of things here. So that would mean if this is 4,000 meters, then this would be right here would be 1,000 meters. Does everybody see that? Well, I can hardly see that, but it's supposed to say 1,000 meters right there, right here. And then this right here would be at 2,000 meters. Not coming out too well. Let's see if I, so this is 2,000 meters. This right here is 1,000 meters. That's better. This right here would be, I'll just pull this up here, 3,000 meters. And then right here, I would have 4,000 meters. Does everyone see how that works? Okay, and now what I'm saying is that this black line here is going to be our thing. So let's just put that into the equation and see what we would get at B. So V sub B, B prime, right? That is going to be, now let's expand this out a little bit here, right? So I'm just going to expand this out a little bit. So just the general equation of V prime. Let's replace a couple of those things. So I got V0 times the cosine, but then what is omega? Isn't that minus 2 pi f? And then L over C. Does everyone see that's a minus up there? Okay. So if I do that and then I look at what it would be, and let's look at 1,000 first, because 1,000 should be 0, should come out to 0, shouldn't it? So I've got V0 times the cosine of minus 2 pi times 75 kilohertz. Don't forget, you got to throw that times 10 to the 3 in there, times 1,000 meters, right? That's the first junction right there, 1,000 meters, divided by 300 times 10 to the 6 meters per second, which is the speed of light. Then that gives me 0. Go ahead, stick it in. You know how I know that? Because 75,000, right, times 4,000 equals 300 million. Does everyone see that? 75,000 times 4,000 equals 300 million. But it's not 4,000, it's 1,000. So it's 1/4 of 4,000, isn't it? So if that's 1/4 of 4,000, then that means I've got minus 2 pi divided by 4. So that means pi over 2. So what's the cosine of minus pi over 2? The cosine of minus 90 degrees is 0, isn't it? Oh, and you know what? Look what we've got right there. So it's 0, isn't it? So I calculated 0, and I got 0. Now let's look at another one. Let's look at this one down here, because we would expect that one at 2,000 to be minus 1, wouldn't we? Minus V sub 0. That's what we would expect. We'd expect the cosine to be minus 1. So let's see if we get that, because so this is at 1,000 meters. So B prime at 2,000 meters is going to be V0 times the cosine, and everyone can see that it's going to turn out to be that, I'm sure. I'm just writing this down because, and you're probably all ahead of me anyway, and of course that would just be 1/2, wouldn't it? 300 times 10 to the 6 meters per second, and that would just make 1/2 of 2 pi. 1/2 of 2 of 2 pi is pi, and minus pi, the cosine of minus pi is the same as the cosine of plus pi. It's minus 1. So that tells me that this is going to be minus V sub 0. We can do the same thing for the other ones here and here, can't we? But why waste our time? Because I've now proven that this works exactly. Now I'm going to cut this out for a second, because I want you to remember that this is at t equals 0. That's the special case that we have up here. What about when t, right? So I'm just going to put that in. T equals 0 seconds. Now, what about when t equals 0.3333 microseconds? And you're probably thinking t equals 0.3333 microseconds. Isn't that 1/3 of 13.33333 microseconds? Yes, it is. 13.33 is the full cycle, isn't it? Now, what I want to find is what's going on later. Didn't I say that this thing is moving in this direction, and it's moving in that direction at the speed of light? That's right. It's moving in that direction at the speed of light. So if it's moving in that direction at the speed of light, then 1/3 of a cycle later, the whole wave should have shifted to the right, shouldn't it? Let's draw that wave having shifted to the right 90 degrees in blue. Does everyone see? I hope everyone can see the difference between the blue and the black. And of course, they're shifted 90 degrees. Now, so what I'm saying is, let's look at 1,000 meters again, right? At t equals 0, 1,000 meters was 0, and that corresponded to that point, 0. Now, at t equals 0.3333 microseconds later, that wave has now traveled, hasn't it? And now the value should be positive V0 at V sub BB. Let's just see if that's right. I'll put it up here. V sub B, B prime is going to be V0. Now it's going to be a little bit longer here, times the cosine, because now what we have to do is we have to include the omega t too, don't we? So now we've got omega times t minus L over C, right? So that's really going to tell me that, in fact, why don't I just write it out that way? So I've got V0 times the cosine. Let's put some numbers in there of point. Oh, excuse me. Wait a second. It wasn't 0.33. What? That should be. Thank goodness I left myself some room. 3.333. Sorry, and I'm sure everybody saw that way before I did. That's right. 13.3 divided by 4 is 3.33 microseconds. So that is 3.33 microseconds minus L. I should probably put another bracket there, shouldn't I? Because I got to multiply this by omega. Minus L, which is 1,000 meters, over C, 3. I'm just going to put 3 times 10 to the 8 meters per second because it's shorter. All right, so we've got that. And then we've got to multiply that by omega, and omega, I can just write that in here. Omega, I'll let you do it. It's 2 pi f, of course, right? But omega is going to be 471 times 10 to the 3 radians per second. So I'm gonna circle that so everybody knows that that's what omega is, but I don't have a lot of room down here, so I'm just gonna put omega and then my brackets and take the cosine of all of that. And what I end up getting is VBB prime is going to be 1 times V0 plus 1 times V0. And you can work that out yourself to make sure that the math all works out here. But of course, it does. And that's what I'm saying. And that's what I was saying with my traveling little coat hanger. Actually, it's not a coat hanger. It's just some wire I found in my room, my little storeroom. So yeah, so I've got a wave. Let's put the wave right here first. And then 3.33 microseconds later, that wave has moved from there to there, right? Does everyone see that? And so the voltage along the propagation line of the electromagnetic wave is a function of x, but also a function of time, because it's changing sinusoidally along x, but then that sinusoid is also traveling, so it's changing with time too. And we have to take both of those into account. And of course, that's how we do it. Now, having said that, what do I really have here? Well, I've like run out of room, but I'm going to cut this little portion out here because I want to finish this off. So I don't have to carry this into the next lecture, which is really a standalone lecture on its own. You know that little minus omega L over C? Well, omega L over C is called the phase factor, right? That phase factor, and it works in any, since we're propagating at the fastest the speed of light, as long as there's a distance, between the two, there's always going to be lag time from the time that the operator puts the signal in at one end of the communication circuit and it gets to the other end of the communication circuit, right? It's a time lag that we've got here. Delta T time lag. I'll even put lag. So you remember what we were talking about, and that's going to be the phase factor. Now, we can look at that phase factor. If you look at that, that's really 2 pi f L over C, isn't it? Well, 2 pi f L over C, well, isn't F times lambda equal to C? So then I could say that F over C has got to be equal to 1 over lambda. Can everybody see that? So this is really 2 pi L over lambda. 2 pi L over lambda. Now, when L over lambda is small, no problem. And that would mean if I was, let's say, sending a 750 kilohertz wave to a satellite, right? Though not even let's say 1,000 meters, right? If I'm sending a 750 hertz electromagnetic wave, where the wavelength of that is 4 million meters or 4,000 kilometers. If the wavelength is 4,000 kilometers and I'm only sending this 4 kilometers, no problem, right? If the wavelength would be something like 40,000 kilometers and I'm sending it 4,000 kilometers, or 40,000 kilometers and I'm sending it 4 kilometers, no problem. If it's 100 kilometers is the wavelength and I'm sending it 4 kilometers, it starts to become a problem. The shorter and shorter the wavelength and the higher in the frequency. Remember that wavelength and frequency are inversely proportional, right? So as we start to get up to multiple wavelength transmissions. Like with the one that I'm showing you here where it's 4,000 meters. Well, let's say that I've got a coaxial cable and I'm only going 1,000 meters. Well, that's still too far. If I'm only, at 4,000 meters, I'm going to introduce things. But what if I'm going not 4,000 meters, I'm going 40,000 meters or 40 kilometers? Well, then all of a sudden you've got 10 of these in there, and that's huge. So you've got to start then thinking about some things. So if L over lambda is greater than 0.1, you have to account for phase shifts. You have to look for reflected signals at the load. And you have to look for other capacitive, dispersive, and attenuating effects. That's what I wanted to tell you. And we'll be looking at that now more and more because let's face it, just about everything that we send is higher and higher in frequencies, and the distances that we're sending them over are longer and longer distances. So we're obviously that's what the next lecture is all about. What are these power loss and dispersive and attenuating effects and the capacitive effects and everything else, and the phase shift and reflected signals and that's what we're going to look at. That's what we're going to start looking at because there is nothing like this. So in reality, this would be in the wouldn't it be great if we could do this? Well, we'd never transmit anything. So we have to go on and look at all the dispersive effects and everything. All right, well, see you at the next lecture.